Professor Mannar sir to come on dais and Professor Rajan Patel. Please come and please come to our guest. Yes. Ji, take a seat. Now I would like to invite Professor Rajan Patel to felicitate our guest, Professor Mannar sir, with a token of appreciation, respect. Yes. Thank you, sir. Thank you, sir. So now I would like to invite Professor Rajan Patel to introduce our guest. Please, sir.
Thank you, Professor Rai Saab. And it's me a great pleasure to be over here today. And first of all, I would like to congratulate Professor Raisuddin Sahab and whole Department of Chemistry to organize this fantastic GYAN program. I think this is a 35, 37 GYAN program in Jamia Islamia. So, and today with us, Professor Moria Sahab, my teachers in IIT Roorkee. I was did my MSc in 2002 from IIT Roorkee, and Moria Sahab taught us and in very well manner in organic chemistry. So, sir, thank you for your always blessing this to me, actually, sir. So, currently, I am director of Center for Interdisciplinary Research in Jamia Islamia, and I'm in charge of CIF facility in Jamia Islamia. And as Raisa have already maybe informed you that there is a visit of all of you there in RCF. So please welcome. I welcome you there. Please come on time. So Professor Moria, currently the professor and dean of faculty affairs in IIT Roorkee, and Moria published more than 170 research articles in peer-reviewed journals. Uh, he has been contributing higher education to the institutions in India as well as in abroad. He is also a editorial member of many peer-reviewed international journals like Inorganic Chemistry, European Journal of Inorganic Chemistry, NJC, and other reputed journals. He has completed many number of research projects from various funding agencies like CSIR, DST, SERB, and ETC. Sir also awarded many awards like Best Teacher Awards by IIT Roorkee, Best Paper Awards, and Good Researcher Awards from IIT Roorkee. He is a life member of many scientific societies. Uh, he supervised more than 30 PhD students, and he has delivered many national and international talks. So, and also, sir is uh, we are thankful to Amara sir. He always come when we required him, and he is very kind and helpful for all of us of you. So, sir, thank you so much for your presence over here today. And so now I invite you, sir. Please deliver your talk to this program. Thank you so much, sir.
Yeah, thank you, Rajan. Because it's my student, so at least I can call him Rajan. Thank you so much for introducing me here, and it's nice to be here actually. And I'm thankful to the organizing committee and particularly Professor Raisuddin sir, who called me here to give this lecture. Possibly, I'm giving the first lecture in courses like Gyan, and I'm a little bit afraid of that. If I don't know if I can be for your parameters up to the mark or not. I'm not very sure. I'll try my best. Uh, see, basically, I'm a coordination chemist. In organic chemistry and coordination chemistry, that is my favorite. And within metal complexes, I'm known for vanadium chemistry. Vanadium chemistry, which is the most difficult one in India, two, three people are doing, not more than that, because the characterization. The one student asked for characterization is very very difficult for such complexes unless you have most of the good techniques available. So with the coordination chemistry, while I was in National Chemical Laboratory Pune, try to learn some catalytic chemistry and then diverted partly myself to some other fields like one of them uh, I'm going to talk today. And well, he's still continuing the vanadium chemistry for last 25 years almost, and I was surviving very well. So I feel that yes, I'm doing something at least. So okay, let's start with. So today I am going to talk about in this lecture that polymer supported heterogeneous metal complexes, how to characterize them, and their catalytic applications in various organic transformations. Okay, very first thing when we talk about the catalysis, I'll take back to like more than 200 years almost, when in 1835 Virgilius introduced the definition of the catalysis. You all know that this is based on the activation energy, right? But at the end, the catalyst becomes free from all and remains almost in the same condition. So with this, if we talk about the catalysis and catalytic products and their utilization, we look at the chart here, catalyst based technology. More than 90% of the products are processes in any field you talk about, whether it's pharmaceutical, industrial, petrochemicals, fertilizers, biochemicals, every field you find application of catalyst. Okay, so all fields is very useful. Me then, when you talk about catalysis, then definitely two things you all know, that basic fundamentals, that what are the catalysts. Maybe one homogeneous in nature, one is heterogeneous in nature. When you talk about homogeneous in nature, you all know that Wilkinson catalyst is a very popular one. We all know that. Jesus salt having plenty applications. Other similar compounds, rhodium compound, lithium compound, when we talk about, they have a lot of applications, and those are homogeneous in nature. And also, you know that many of the heterogeneous now catalysts are known. So, which of them is really good? That question comes. No doubt, homogeneous is having tremendous applications. You all know that Ziegler-Natta catalyst, simple reaction polymerization, Wilkinson's catalyst for homogeneous, for what is called that hydrogenation and that hydroformylation reactions, etc. Okay, but whether the heterogeneous catalysts are good when we compare between homogeneous and heterogeneous, definitely there are some benefits with the heterogeneous catalysts. What are those? They can be recycled, they can be used time to time or several times without going to like diminishing their properties. While homogeneous catalysts, well, they are good, but at the same time they have a problem in separating them from the reaction mixture, because at the end we have to quench the reaction by decomposing the catalyst, because separation becomes very difficult. And then even separation becomes difficult, then either you continue, or when you need to stop it, then you have to break down the catalyst so that you can recover your catalytic products. So what is the solution for that? Solution is that make the homogeneous compound heterogeneous in nature, then it becomes a really useful. So you can have a, you can enjoy the property of homogeneous as well as heterogeneous both together. Then recyclability becomes no issue at all. So then it becomes easy separation from the reaction mixture. You can just simply filter it. Okay, and they do not produce normally the waste. That is the beauty of the heterogeneous catalyst. And also, when you talk about the last, meet the industrial demand of recyclability, because this is one of the major issue these days, whether catalysts are recyclable and reusable. Stability, recyclability, and reusability. That is the major issue every time we talk about. Okay, so let's see that. I have tried. In fact, in India, I was the first one when I was a PhD student about to leave. My supervisor said that why don't you start this field? Well, after PhD, getting PhD degree, you don't take interest what supervisor says by that time. That is the fact. Today, that fact is fact. All right. But he said, will you start it? Well, I was forced to start because I had to get recommendations, right, to get somewhere postdoc or something. I started it. I learned some chemistry there. That was in my mind. And then next student we joined the group. He did the all other chemistry. I just handed over everything, gave all know how the this way to proceed it. So we started it. But when I started my journey for postdoc to the lecturer or assistant professor at the faculty position, I forgot that because I had to learn some more things. When we came back, then I thought of why not, after having some experience in a catalysis from the catalysis division of National Chemical Laboratory, I thought let's start it. So we found this is one of the simple material. It was gifted from the Thermax company from the Pune. They gave me like 500 gram this materials with this kind of a structure with chloromethyl polystyrene cross linked with divinyl benzene. So then I started thinking how to use that. So we started with this is a very simple reaction I would like to show you. You has this is CH2Cl group and the NH group there is available. They can condense very easily to form a covalent bond. And that was the beginning of this very simple ligand, very simple chemistry we started with. And since vanadium was the favorite one, let's start with the vanadium because I know something. So that was the output of that, and we could prepare assembly compound by this way. Prepare first the attach your polymeric materials with the ligand and then do the metal chemistry, what is usual chemistry. So this way it worked out. Other way that when you look at here, you have a COH group, OH group and carbonyl group. COH group is more reactive because you not CO minus that forms very easily. So the formation of the covalent bond between polystyrene and the COH group was very easy. So we started with this one stepwise formation. First you have to react with the say formyl salicylic acid. Then the next step like shift base chemistry, you react with the amino alcohol or amino acid compounds and then do the reaction with metal salts. As usual chemistry we do that and it worked out and we could prepare that compound. Okay, I'll show you some other way also. The same way when we extend it, then the question comes how to characterize. Very first question. Characterization not an easy job because we don't know how to characterize polymer. Polymer IR will not give you much information, but since metal ion is attached there, nitrogen also is present there. First thing we can do that elemental analysis. If that gives you metal content, if it gives the nitrogen, then according to the formula of the metal complex, simple coordination chemistry fundamentals, we can calculate the metal to nitrogen ratio. Based on that, we can fix at least this is the compound, possible compound. Okay, so based on that, this has been fixed that, and you will see that there some nitrogen percentage, vanadium percentage. So when you convert into millimole, then you see the 1.3 to 1.06, almost like 1:1. So this is possibly the 1:1 complex formed in the reaction mixture. Okay, then the other characterization can be done. Other way there, you have a ligand here already available, react with the CH group, and look at there, then you form the all the way, and then do the reaction with the starting precursor, and then finally, see, this is one of the way you can isolate right there as a methoxy derivative, or when you pass excessive oxygen, then methoxy group is lost and another oxygen group comes, the diaxo. Why diaxo? We are more interested because their characterization becomes very easy. Why characterization becomes very easy? Because in the IR spectroscopy you are familiar with, and you also had some exposure of the IR in the previous lecture, where here we have a C vanadium double bond and the both oxygens are in a cis position. So cis position means if you have a V double bond O, around 900 centimeter inverse one peak can be seen there. Maybe because it's polymer material that may be weak, but when you have the two double bonds and the cis position, there two signals can be seen very easily. Cis and trans, you know that the fundamental principle. Okay, so then characterization becomes very easy, and you will see that after all this good thing came out, and we are able to publish it. Okay, another way that we have a NH group in the very first slide where I showed you that, then now we have experience and we can go all the way around and prepare these metal complexes, different kinds of all sorts of compounds we can prepare very easily with that. Okay, see the another one. See, we have a SH group and COH group. SH group is weaker in finding S minus bond, but CO minus is very easy. So this we worked out, and we could prepare the another ONS type of ligand connected with the vanadium and finally attached with the polymer to make it homogeneous in nature. Now, see the characterization a little bit given more detail. Ligand to metal ratio, you can find out this is the two formula given where you can calculate the metal loading and you can calculate the ligand loading. Based on that, then the stoichiometry can be fixed of these compounds. See, this is another way. What I showed you that everywhere either CH group or NH group or OH group were present to coordinate to form a covalent bond with the polystyrene. Here, this is another way around. First, functionalize the chloromethylated polystyrene with, like, see, you have a their imidazole type of molecule in the NH. You know that it can coordinate, it can react, form a covalent bond. So, convert the polystyrene into the that benzene hooked polymer, and then now there is one nitrogen which having lone pair of electron which can donate the lone pair of electron to metal center and form a metal nitrogen bond. So that is strategy worked out very good, and we can also prepare this way the another molecule heterogeneous in nature, and the since covalent bonding is with the vanadium is there or the nitrogen is very stable, doesn't lose very easily unless having very drastic condition. Okay, then characterization comes in the picture. How to characterize it is a difficult job. When we started this chemistry in 2002-3, we were lost how to characterize it. We were hopeless how to characterize it. But slowly the techniques came during that period when IIT Roorkee had only FE, not ACM. It was not available, but we could see at least there. The later the ACM also FE with ACM came, and there the beginning you could see the image of that, and that image gave some information. One is very light and one is a little bit dark in color. That gave some indication that yes, the heterogenization has been occurred, and the metal complex has been attached to the polymer with the covalent bonding, and then later through the SEM energy dispersive X-ray analysis we could see whether if ligand is there by looking at the nitrogen percentage, and then vanadium is there by looking at the vanadium percentage, that we were sure now that well this is the metal complex is anchored or covalently bonded to the polystyrene, or in other words that heterogeneous metal or catalyst has been prepared successfully. Okay, also we can record where this is a solid material insoluble in polymer is insoluble in any solvent. However, we can compare the UV visible spectra with the regular homogeneous compound, but since the material is insoluble, how to record the UV visible, that is a challenge. So we found one techniques where the metal complex, heterogeneous metal complex, is grinded very, make it a powder, and then add some nozzle, make it like a paste, semi-solid, and you just simply stick on the cubit, whether you have a quartz cubit, you paste it. So you have a one simple nozzle pasted and other one having your metal complex pasted, and do like a regular UV visual spectroscopy, and you can get some feeling or some observations through that one, and that worked very well. You have to adjust concentration several times, but you should be able to get the visual and UV visual spectra of these compounds very well, and can have some information after comparing with your homogeneous analogs. Then EPR state works very well. EPR in the solid state. EPR also can be recorded in the solution DMSO. Just I mentioned that by grinding your sample into first and then put it in the DMSO, the suspension, and freeze it -70 degree. That becomes almost like a solid, and you can record the EPR. EPR worked very well because EPR is very sensitive to the metal ion. Okay, so see 8 lines EPR spectrum, and you will also do that in the two different way. One is solid, one is dissolved in DMSO. You know, at -70 with the homogeneous and the heterogeneous both are compared here. You see that all signals whatever available in the homogeneous system is available also in the heterogeneous system. Means the compound, if this is vanadium 4 with only one unpaired electron in the d orbital, so easily can be seen through that, and that can be interpreted that we have a metal complex form into the heterogeneous system. Now, see, this is one of the technique that is called the 51 vanadium NMR. It's a very difficult challenge because it doesn't give really. We tried here at our place now. This was recorded from the Portugal, from University of Lisbon, that they could record it, but we tried here. We have to run several thousand scans to get 51 vanadium NMR. So that was the difficult challenge. We dropped that idea. But anyway, that give you the feeling that we can also record 51 vanadium NMR. Proton NMR is not possible. C30 NMR is not possible. The reason you know very well that because a lot of carbon and hydrogen in the polystyrene. Okay, that is not possible. But metal center that can be detected here, and based on the peaks observed at say minus 535 in this compound, and upper one there is 535 and also minus 504 signals, major signals, that is for the diaxo, and then the other signal that came that we interpreted it based on the literature that this is the possible interpretation of this 51 NMR, but it worked, and that showed that we have a metal center or we have a metal complex anchored or immobilized on the polymer support. All right. Now, after doing that, now we tried different catalytic applications. Characterization now by doing all these different using different techniques, we are familiar with that the compound has formed and always compared with the homogeneous metal complex. So we give the idea how what is the structure possible in the immobilized materials. Then we started some catalytic activity. I'll show you some simple catalytic activity here. That is one of them very popular one is that oxidation of sulfide, organic sulfide, because this oxidation, if you look at that sulfoxide and others, they are sulfur drugs mostly having various double bond or two oxygen, okay, double bond, oxygen, sulfur, oxygen, diazo group. So we tried it and see the conditions can be fixed, that is called the optimized condition to get the maximum conversion or maximum oxidation. So what we can do, we can optimize using different loaded of different loads of the catalyst. You can also change the what is called that oxidant. You can also change the temperature. So by doing all these things, once we get the highest conversion, then we can check all our catalysts under that particular condition. We will see that we have four different catalysts used here. Some of them are polymer supported and some of them are no polymer supported, but the activities can be seen here with time because this is recorded at every like half an hour using gas chromatograph, and conversion can be seen that, and the details can be seen here. See the polymer supported and comparison with the homogeneous catalyst. You see that polymer supported catalyst giving very good conversion along with good turnover frequency and sulfoxide and sulfone selectivity. You can also calculate through the gas chromatograph by using internal standard. We are not familiar those days how to use external or internal, you know, um, standard. So what we have done, we have used the uh, what is called that area under the peak, that gives approximate good, good enough data to approximate that these are the conversion, these are the selectivity, but it worked very well. And also when we compare the catalyst with, along with, we can see we have a vanadium 4 center. A vanadium 4 center is EPR active. When we had H2O2 is oxidant, it oxidizes vanadium 4 to vanadium 5, that goes from D1 to D0. D0 means there is no electrons, so you should not be able to see the EPR. So when we have done that, when you look at there, adding A, B, C, D, some small amount of hydrogen peroxide, some more peroxide, what happens here? The signal is going weaker and weaker and finally almost becomes like a flat. But when we add methyl phenyl sulfide into the mixture, again record the EPR, what will happen? The peroxide species formed during the reaction with the H2O2, the oxygen is transferred to the sulfide slowly, and sulfide is converted to sulfoxide and sulfone. So oxygen is, you know, you are taking out oxygen from the peroxide species and then converting back to oxyvanadium 4. So your then signals are again regenerated. That clearly shows that oxygen is transferring from the peroxide species to the substrate and is converting to sulfide and sulfone. So that gives very good idea about the possible mechanism, during the reaction, how is it going on. Similarly, 51 vanadium techniques, as I mentioned, that it is useful and gives some signals. So this is done by the homogeneous system only, not with the heterogeneous system, because heterogeneous system gives a trouble. But you can see that in the beginning there are two signals, one major signal that is for the uh, after addition of this is one of the diaxo compound. So when you have a diaxo compound, you will see one big signal, and some any other species, isomeric species, small signals can be seen right there. And then when you add H2O2, you should be able to see another peak generation of the peroxide species along with the diaxo. So look at there, the peak around that is 600 something, 579, another peak is generating. Okay, means diaxo is going to the peroxo, and when you add a substrate, then the peroxide species will break down as soon at the top of the compound. You will not see the peroxide species formation in the solution. So that clearly indicates that there is transfer of oxygen from there. So peroxide signals is going back to the diaxo, giving only the major two signals what is expected. Okay, and the other signals, because in the solution that will not remain only the diaxo, maybe some other species forming, maybe some DMSO interacted species, maybe some other species. So more than one signals are always expected. But that gives idea that this is the way reaction mechanism going on during the reaction. Okay, so based on that, the reaction has been proposed that the where diaxo species is going to the oxohydroxide species and then going to the peroxo and with H, and then oxygen is transferring, giving to sulfoxide and sulfone one by one oxygen transfer. So reaction mechanism can be proposed for that reaction. Okay, now after getting the idea of the oxidation of sulfide, this is one of the very very important project where when we have a organic sulfides, those organic sulfides found in gasoline, petroleum products like our diesel and petrol. These are the challenges for the industrial people like IIP Dehradun, Indian Institute of Petroleum. They are doing a lot of research for desulfurization. That is called desulfurization. What they are doing is basically oxidizing organic sulfides to the sulfoxide or sulfone. Okay, so they are making it soft because these are the materials which are actually creating problem. These are the mixture present into their mixture. So what we have tried here, we have tried to oxidize different organic sulfides. Different types of sulfides you will find there, and of course we have used this catalyst. Okay, how have you done that? We have prepared a solution of like a 500 ppm in a simple N-heptane. So you are making like gasoline, you are making like petroleum products. Okay, and then we try to catalyze the reaction and looking at how much ppm sulfide is remaining the other way around through the gas chromatograph, and that gives wonderful idea that how much conversion had done or does desulfurization has been done. So when you look at that 500 ppm initially concentration was taken, and after desulfurization this is the ppm we obtained it. So that shows that the sulfur removal or oxidation of the sulfur has gone like this way, like almost like 87, 88, and 89%. We are able to demonstrate it, and that actually give you a very good boost up in this chemistry, and we were able to publish this paper in organic chemistry. Very simple chemistry, but it worked very well. Okay, so you will see that also with the regular homogeneous catalyst, the conversion is very much less than their heterogeneous system, and the beauty of that was that is recyclable. We could filter it simply, wash with the acetonitrile, dry it 120 degrees in like a regular air oven, and then reuse that. It was very good, reusable. So that worked out very well. Now, see, this is another reaction we have tried with the benzoin. Benzoin gives you four different products. those products can be analyzed by gas chromatography, different products, and based on their GC mass analysis, mass spectral analysis, we could assign all these products like going major into the benzyl, then we have methyl benzoate, benzoic acid, and we have a benzaldehyde dimethyl acetal using this catalyst. Okay, and details are given here. Again, we can optimize the reaction conditions by varying, say, the amount of oxidant, amount of catalyst, and then we can analyze it. The analysis is a very, I mean, it's not easy, it's time taking because every product at every half an hour interval you have to use it and characterize using just gas chromatograph. So for 400 minutes continuous analysis for every half an hour and analyze those, and then it can be seen that benzoin is going from almost like 90 plus percent is conversion, and then the different products are forming, and you will see that benzyl initially forms in a good amount but slowly converts into other different products, which is expected because then the changes in the that one from the benzyl to the other products are expected because further decomposition of that, further oxidation of that. So the all four products have been analyzed that, and see the conversion here, and then the product selectivity that benzyl is still the higher side is not that bad, but along with that your D product, that is benzoic acid, it forms a much, that is expected that because it's further breaking and oxidation of that one. This is parachlorotoluene. This reaction gave us very hard time because this parachlorotoluene oxidation is very difficult. But we could oxidize, though yield is percent conversion very, very poor, but we observed that there are at least 5 different products. Characterization of products itself is a challenge, but we are able to identify with the help of gas chromatograph, and these are the catalysts used for that. And when you look at the data here, the conversion is, when you look at the how much? Maximum 12%, no, not much conversion, but whatever conversion based on that, at least the different products can be analyzed because gas chromatography require only the ppm level concentration. There we can go for that and we can characterize that. Okay. Now, as I mentioned there, this stable catalyst EPR can be very helpful, so I will not go for that. Then this is a regular like a substrate across the world people first start with, whether cyclooctane or cyclohexene can be oxidized using catalyst. It's standard. We have also done that. And these are the catalysts used here is shown. It is some copper catalyst and vanadium catalyst, and this gives at least 4 products. Okay. Those days we were not much familiar with the catalytic system, but still. Then later we have improved that, how to improve the conversion of the cyclohexene, conversion of cyclohexene to epoxide, because epoxide is a useful product. So we have later found out how the yield of the epoxide can be improved, but whatever data we had during those period, and you will see that at least 4 products are there where we have a cyclohexene oxide, cyclohexanol, hexanone, and cyclohexene 1,2-diol. Okay, and product analysis may be given in the next one. And then this reaction we have done. This is one of the very important reaction. Why? See, it's so simple reaction. I had given this project to MSc student. MSc student in the 4th semester for the simple project. Just see that if the reaction works or not. See, this is bromination using potassium bromide. One of the very important reaction shown by the that is called enzyme haloperoxidase, vanadium haloperoxidase enzyme. So vanadium can be used as a model system for haloperoxidase activity, where KBr in the presence of S2O2 and acid can be converted, can do the bromination. Okay, you remember the Br minus is going to Br plus and then attacking it and making the brominating the product. Okay, so reaction worked out very nice. Simply take a water, add a small amount of catalyst, as much small you want, just add 2 crystals of the homogeneous catalyst and add a sulcidated water. Sulcidated is not soluble in water, that is like a suspension, and when the reaction starts you will see the white solid coming out. This was wonderful to see, so excited to see this chemistry is working very well. So we tried that we using this catalyst, and then I gave this real project to the our one of the MTech student, and you will see that the paper in catalysis communication worked very nicely with simplest reaction, I would say that. And still we are using that, what is called the basic principle of hello peroxidation activity for the good molecules actually. Okay. Okay. So what? So you can look at the conversion. Conversion is more than 80% in most cases. And we have a 5 bromose salsylate. That's a fundamental principle. Okay. That 5 bromose salsylate is giving, and some other products. Other products are, those days it was very difficult to characterize because that time we had no GC in our lab. Usually used to go to the chemical engineering, or I had sent particularly for this one sample to National Chemical Laboratory. So they gave, this is the major products, other products we are not bothered about that. Anyway, that we still worked it because that gave a very good yield. Okay. And then this is usual uh, alkene oxidation reactions. You will see that. Okay, terminal alkene that giving you 5 different products of all products. What we expect that styrene epoxide is the most possible product, but that is converting into, in fact, the ethyl oxide, sorry, styrene epoxide forms at the very beginning, but it goes to different products to further oxidation. Okay, and this is the catalyst used for that one. So those very traditional reactions. Then we thought, okay, let's try some really organic transformation to do some organic chemistry here. So one of the reaction that is called the hydroamination, another one is oxidative amination. What we have here, we have a alkene, we have a primary or secondary amine. In presence of catalyst, you find two products. If you know that Markovnikov and anti-Markovnikov rule addition, you have a two products, Markovnikov and anti-Markovnikov. Which one should be higher in yield? Because anti-Markovnikov is more favorable because less steric hindrance presence in that, and that gives you two different products. Okay. Similarly, oxidative amination. Again, you have a primary or secondary amine, you have a then oxygen now, other one is without oxygen. So there again you get two products, and what is called that anti-Markovnikov is always higher in yield. So one by one these reactions will show the product here, real products. We get the two products. The 4 reactions are shown here with the secondary amine. Okay, and one side is primary, other side is secondary amine, and you see the products. Okay, and we have LIG. This is the catalyst used for that purpose. Okay, and see the conversion very good, giving you almost like 65 to 80% conversion. And then Markovnikov or anti-Markovnikov, as I mentioned, the anti-Markovnikov always higher yield because of the uh, less steric hindrance available during the reaction. Okay, so all data are presented here. And this NMR 51 NMR spectroscopy, by using the homogeneous analog, we are able to predict the mechanism. Because when we do that, see, in the beginning we have a pure catalyst, homogeneous, and then when you add diethylamine, you see the changes because diethylamine is interacting with the metal center, giving the change. And then you add also styrene, then again change you will find that. And when you add excess of styrene there, then the almost original position coming back, that shows that reaction, that amine in the beginning interacting the metal center, and then in the presence of styrene, that product is forming, giving you the final products. So based on that, we have tried to propose this mechanism here through Markovnikov and anti-Markovnikov. Both products are shown here how it forms. The possible mechanism always. Now this is for the oxidative amination, where all products are shown here that forms catalyst. This catalyst has been used there, and see that conversion is approximately 70%. Markovnikov and anti-Markovnikov. The same way, the yield of anti-Markovnikov is better. Okay, so of course, based on again the 51 vanadium NMR spectroscopy, we were able to predict the mechanism for this compound, this reaction. So up to that period, we have tried to, summarize, review all these studies. One of our review here that is published in say 2011. Then we based on the students, of course, the chemistry proceeds. If you don't have a student are not interested in polymer supported, doing the vanadium chemistry, taking the challenging job is better. This student, one of our Bengali student, he was running out from doing the all good vanadium chemistry. So I gave him, okay, let's do with the polymer chemistry. And you do this, you see that this is molybdenum. Okay, another change. But the molybdenum means chemistry is not less important. Chemistry is again important. Chemistry, I will show you how. So the preparation, now you can feel that preparation is not much difficult. This is just a generation gap to show the fancy way the polymer, that's all. Okay. And well, of course, the generation is more intelligent, giving more because we have everything now on the laptop, everything available. You can play with, you can design, make it a good design. Okay. Because these days you need chemistry along with the design also. You will find organic molecules, if organic students are sitting there, they will also color the benzene ring. I hate that. Why are you coloring benzene ring? But the student do that. Okay. So that's the way. So the chemistry work out very well. But here we have used starting material MOO to ACSE2 to prepare first that particular compound, dinuclear compound. And then in the bottom and you the hanging is that ethyl benzimidazole group, sorry, methyl benzimidazole group where NH group is available. So from there, this covalent bonding can be done, that can be formed there, and so this is highly stable. Now we have more techniques available, right? Those days techniques were not available. So now FESM with EDS also you have a what is called that metal content more better way you can determine it. Okay, so all colored pictures and you have see these things are shown here, metals, and between these figures you will see that the uh, elemental mapping can be done very easily because you can see the different dots and then everything can be corrected. Okay, so elemental mapping gave a very good result, and this with FE those things can be seen very clearly. Earlier it was only black and white system, now we have a colored one. So the better way it can be seen. Okay, because the changing world, better instruments, more sophistication, more precision. Okay, so and then UV visual, you will see that as I mentioned, the UV visual very easy to characterize, and also for IR, this system is very easy to characterize. Okay, we have a diaxo cis system. It's same way IR. I have not shown IR here because it's a simple technique, but UV visual can be seen. There is no electron in the d orbital, but still charge transfer transitions can be seen. And also the bands due to the ligand that is expected only the UV region, all can be seen very easily. So we have characterized it. Say the more detailed way, the simple way it is given here. Okay, and then for the other metal center. Oh, thank you. But it's too cold, I guess. Okay, so all elemental mapping can be done. Okay, after that, look at there. Best way. Okay, do the elemental mapping, go for that and characterize it. Now what we have further? XPS. XPS gives you perfect information about the metal ion present, because you will see that all peaks can be seen for the even carbon with the nitrogen. We have a carbon and double bond, everything, and also metal mapping. So it XPS gives all information whether the pseudo ion group is present there, nitrogen present there, carbon attached to the nitrogen present there, also metal center present there. So all information can be gathered together for perfect characterization. Also the atomic force microscopy, AFM. When you do the reaction in the beginning, when you have AFM, their metal centers, everything are aligned well. Sharpness you will see that in the beginning, and then roughness height you can see that here. Average surface roughness 16.21, and when you have a PS1, that is catalyst, okay, then 4.0 surface roughness has gone down because of the complex formation. All right, and then also you will see that the after recycling surface roughness has slightly increased because part of the things has gone, possibly the leaching, but those were present on the surface that is gone, but still metal is present, the metal content is very good in that one. So all PS1 PS2 three catalysts were prepared, and then by getting the surface roughness we can get the idea how much it is, I mean, anchored there, and after catalytic cycle is going away or not. So that can have idea. Then this is one of the reaction we have tried it, because why we have tried this, you will see that all is biomolecules. Okay, chromine, cyanochromine molecules, these all are having different biological activities. Okay, so idea was here, can we do the similar chemistry we prepare through catalytic reactions, that is called multi-component, one part multi-component reactions. All organic chemistry student must be familiar with that, where three components can be mixed in the reaction mixer. Sorry. And when you have a catalyst, do the catalytic activity and get the products. So look at here, we have taken three different uh, that is molecule like coumarin, resocinal, and 1,3-cyhexanedione. You have a malonitrile and you have aldehyde. Okay, and three different types of reaction we have carried out, and say yield is giving really good, more than 85% yield we are getting. And the beauty of this reaction is the selectivity, 100% selectivity, pure products. You do not require chromatography, because organic chemistry means chromatography, that is sure. Any compound you make, heterocyclic compound, you have to, unless you characterize by purify by column chromatograph, you are not good to pure products. But this is giving almost like 99 plus percent purity. Okay, so we have prepared this compound, and to prepare that compound, we have just simply excuse me, optimize the solvent. Okay, so solvent, when you look at there, ethanol gives really good result. And ethanol is supposed to be very simple, what is called that a solvent, easily available, and it's a green solvent. Some reaction was what in water, and some even without solvent we can go for such kind of reactions. Okay, so we used it, and then using simple ethanol, then we have optimized all other reaction conditions like catalyst amount excuse me, catalyst amount, time, how much time it takes, whether it's use a reflux temperature, other temperature, and yield. You will see that it's going almost like भाई ये तो गला ही खराब कराएगा है। आप चाहते हैं कि हम यहाँ से जाए और गला खराब करें? हाँ, मुझे तो यही लग रहा है, साजिश। Okay, so you will see that the simple with how much catalyst you have, a 10 milligram polymer supported. 10 milligram is a very small amount of catalyst there. Okay, so its reaction is going up to like 91% with 199 plus selectivity. Okay, and you see that all compounds we have done it with homogeneous, we have also compared, and also the last one are the recycled catalyst. So you got the conversion, it's going very well, and catalyst can be recycled at least 5 to 6 times. We have done that and working very well and getting the good result. How to recycle it? Simply we can filter it out, because its polymer beads are there. So using simple filter, because organic dissolved in certain solvent where your product is soluble, catalyst is insoluble in any way, that can be filtered and can be reused. Remember that when we say reuse, if you are filtering it, being a human, we are going to lose part of that catalyst. So in next cycle, what we have to do? You combine two such cycles, products separated, the catalyst of two such cycles together, and take the same amount what you require it, and then you can proceed with that very easily. Or you filter it out, add substrate and products right there, and we can do further reactions continuously up to 3 to 4 times very easily. It works very well. That case reaction will perform little poor and poor after 3 4 cycles without separating from the reaction mixture. Only what you are doing there, adding the solvent, removing the products, and then again adding the all substrate, catalyst, oxidant, etc., going for that reaction. It works, but so that reaction yield performs poor. But you see that all products we have different products, you know, we have prepared with different derivatives, where we have electron withdrawing group, electron donating, all are there. Electron withdrawing group was a bit little better, getting a better yield of that, but giving you good things with recyclability. This is one of the good part. Now, so different, what is called that study, we were able to propose this mechanism, because this way we have also tried to isolate intermediates to propose this catalytic cycle. Okay. Now look at this. 91 to 85, where we are using continuously without removing catalyst from the reaction mixture. Only this filtering out the catalyst, sorry, filtering out the products from there and reusing right there. Okay. Now, after catalytic runs, we have tried to characterize again all materials by all spectroscopy IR. When you look at the 911 and 943, that is for this cis diaxo compound. We have done UV visual, we have done FESEM, elemental mapping, everything, and also we have done XPS, getting all peaks, whatever possible peaks were there. Okay, so we have a more what is called the characterization techniques available. So definitely quality of the materials your study has gone up, and when you see that published in chemistry European journal, a very high impact factor. Okay, oops, saved. All right. So now this is the another simple molecule, and then immobilized on the polymer support. Now the advanced technique and student third generation, right? All right. So this is the molecule, and then see TJ characterization. You will see that very stable. That means metal oxide has formed, because polymer means 100% has to go out. So whatever metal oxide, from there you can have estimation of metal content, as well as through ICP-MS you can have a metal content. Through FESEM elemental mapping you can have a metal content estimation, and you can compare all three and should get all three almost same. All right. In IR, two bands, that is for the vanadium diaxo group. It can be seen. UV visible. Now I vote for that. And now this is another reaction that is called hydropyrimidine. Hydropyrimidine owns. Okay, hydropyrinones. This is another biomolecule, and we have tried this reaction with three components: aldehyde. Now we have a urea, and we have a ethyl acetate, or you can say the beta ketoester, and the product formation there. The reaction works very well. See, the conversion is going almost like 85% yield, and the beauty of this here is that you can separate the product by dissolving it and then just evaporate it, you get the compound, and you can crystallize it. You don't need to go for column chromatography. That is the beauty here. Okay, so the isolated yield in optimization condition is going almost like 95%, and all products, and this is both way. We have isolated yield, and then we have a almost crystallize that, or recrystallize, you can say that simply. Both yields are given here, working very well, and it's pure. That is the beauty, it's pure. Thank you. You thought of me. Yeah, thank you. रईसुद्दीन साहब को तो अप्रिशिएट नहीं करेंगे, उन्होंने ठंडा पानी पिलाया. Yeah, we have all compounds prepared, not only plenty of derivatives, we have prepared it. Okay, and then we have also tried to check the recyclability. It's going keeping very well, keeping very well. If you want to have a 95% conversion, then what we need to do, two cycles, as I mentioned, that isolate, separate the catalyst, combine together, and take the exact amount what we had taken in the beginning first time. You will get almost same amount of conversion there. This is just by separating it and doing catalytic reaction within the reaction flask. Okay, so that can be done, and based on the different study, we have tried to give the, through DFT. Actually, we have taken help from one theoretical chemist. Through DFT, we have tried to give the catalytic reaction mechanism for that. Okay, now I'll move to the other products. See, look at here. Plenty of compounds are shown here. This is related to 13254 trisubstituted imidazole. Imidazole containing molecules, when you look at their biological activity in all, whatever you think, even in all directions, these are very well known. So biomolecules, the key imidazole are there, are in all compounds. So how to prepare such compounds using our catalyst? See, this is another catalyst. We have designed it. Okay, and this is for the homogeneous compounds. First characterize it and then compare all activities. Now you know that how to prepare this compound by covalent bonding with that NH of the benzimidazole. Okay, and this is the one where the simple reaction is shown is simple representation of the reaction where you have aldehyde, you have a diketone, different one, and you have a ammonium acetate. When you use urea, that will give a different product. When you use the some other ammonium compound, that gives different. Here we are using ammonium acetate. Ammonium acetate giving you the ring like imidazole type of compound. Okay, and then all sorts of product with the different derivatives. So electron withdrawing on the benzaldehyde, electron donating on the benzaldehyde, all can be used and the different products can be prepared. Beauty of this one is the last component, look at there. We have a bisaldehyde, terephthalaldehyde, that works very well also. There are two different aldehydes on the both sides and both aldehyde groups are giving two different benzymetal group joined through the in a para position and thus giving you and also in the good yield. It's not bad yield, 83%. And beauty is that it's a pure compound. You don't need to even crystallize at this point. You can get the NMR. Well, if 500 NMR is giving no impurities, I believe that this is the best. 99+ % purity of that. Okay, and they say that complex 1, 2, 3, 4, and then recycle 1, 2, 3, 4, 5 cycles. Working very well. 93 going to 84, but it means 84% is still after fifth cycle means a good one and can be used as an industrial catalyst. I believe that if very well done under those conditions. Okay, so they based on different studies, catalytic reaction mechanism, that is important to give that. The reaction mechanism has been performed where if you are a organic chemist, some of you will read that Newangel reaction, Michael addition, other things, all basically based on those what is called the reactions known already. This kind of reaction mechanism has been given. Okay. Now this is another molecule. Okay. Now here what we have, benzyl parazolyl barbiturates, and other one is okay. This is one of them actually, and benzyl parazolyl barbiturates, and you have bioactive pyrazoles. Both are actually very similar molecules with a small difference only. You will see that. And again, when you look at their properties, with the having that key group of that barbiturate or that pyrazole and their applications, we thought that can we do the reaction, catalytic reaction, and prepare those compounds. So now here is another vanadium compound immobilized on the polymer surface, so heterogeneous compound. And this is one of the reactions shown here. We have a beta diketone, we have ketoester, and we have a hydrogen hydrate. Oops, NH2 one, that 2 has gone, right? Do you see there? NH2, it should be NH2, NH2, hydrogen, NH is shown there. Okay, so it should be NH2, and then you have a like of this another molecule there, benzene hydroxyl group, and then this goes the reaction like this way. There is a controversy in the literature where people say that this actually they what is called the cyclize and give you the cyclic products, but we observed that this does not form cyclic products at all. It gives the like in any this ionic compound, and that is stable even at any condition. Doesn't go under cyclization. Okay, so the scanning of the solvent and then the catalytic reactions and reaction products. All reaction products, you'll see that yield is very good. And again, the beauty is that yes, we can prepare it with a good purity. We have recorded only just by simpling it, what is called that filtering it, and we have also recorded after simple crystallization. And after crystallization, these yields are reported and giving you very good yield. Lot of products, all with different electron withdrawing and electron donating group. Okay. Then only one case, that is exception. Why in this case? Because here we had hydroxyl group that is related to salicylaldehyde. In case of salicylaldehyde, only we observed the cyclase. It was very unique one. In all other cases, we did not find cyclization, the only one. Okay, why it happened? And also, since it was different, so we thought of okay, let's try that, have a crystal structure of that because it's crystallized out very well. And so you see that only cyclization. This was exception to all other products where you have only benzaldehyde with different derivatives. Okay, so and then you have the other one that is now paranoparazole. Again, this is called uh, four component reaction, but in this case, since see the same reaction is carried forward, NH2 NH2 should where is NH happened. Okay, and then these two reacts with and form this one like in the previous case, and then when you have malonitrile and aldehyde, that gives you this product. Very similar product like earlier, only we have changed the what we have changed here. In that case, I will show you where it's gone. We have a triketone, and there we have changed it to the other one, simple aldehyde. So that becomes paranoparazole. And we can prepare all sorts of compound, and at least almost like 15 compounds we have prepared it. Okay, part of that are shown here. Beauty here is that to propose the reaction mechanism for such compounds, if one can isolate intermediates, at least few intermediates of the catalytic cycle are characterized by any maybe GC-mass, maybe HRMS, and then it becomes better. So what we have found out that in the beginning, like a beginning, when you combine these two, this give you the intermediate which can be isolated, and these two reactions, NH2 NH2 is known, and this forms the intermediate can also be isolated, and these two compounds intermediate can be reacted again in the presence of catalyst and give you the product. So you have we have isolated one intermediate and second intermediate, right, two intermediates in between, so that gives you the perfect reaction mechanism, that how the reaction is moving during the catalytic cycle. Similarly, for the other paranoparazole, see we have the reaction of this aldehyde and malonitrile give you the intermediate which can be isolated very easily and characterized. And see in these cases at least four compounds we have isolated and characterized it. And the other one which is well known in the previous section I showed you. And these two reactions can be combined together in the presence of catalyst and give you the product. All right. So based on that, this is the reaction mechanism. It looks very complicated. Okay, and believe me, drawing this simple mechanism took me a lot of time. Any student, we spent days and days how to give this mechanism because characterization of intermediate, isolation there, characterization, and then finally putting in the form of a mechanism as a difficult job. Okay, this is under investigation still further. We have just submitted it. I don't know the future of this. We have submitted for publication. Okay, so I think almost 1 hour over. Huh? So finally, I'm coming to an end. Definitely, uh, this whole works started. I think we started in around 2002, and journey of the 23, 24 years with the help of only the Thermax. Thermax, they are preparing resins based on the polymer in the Pune, and two times we got 500 gram gift of polystyrene from there with almost chloromethylated. We requested or we needed, they prepared it, and then after all and also they give it. So we're really thankful to those because of this polymer, we're able to publish, I think, more than 50 papers in that area, and all good quality journals we are able to publish it. Because chemistry we learn it, and we are the only one major in chloromethyl polystyrene across the world. We are doing it well recognized. Of course, the DST, Science and Engineering Research Board, now it has changed to NRF, and Council of Scientific Industrial Research. DST was so generous in 2010 because after doing lot of catalytic chemistry, we requested for gas chromatograph. So exclusively for our lab, we got a gas chromatograph devoted for my research group, and it's still working very well. So 2010 we got it, almost 15 years over. Normally, doesn't instrument doesn't survive, but it is surviving. It's still, and whole department is using. I allow to whoever wants to use it, and it's working. If anyone interested here can come and use it. Most welcome to all. And thank you so much for your attention. Yes, any question, please. Yes, you got all answer your questions in your mind. But yes, sure, please. Uh, Polymeric metal complex in polymer. Ah, okay. I didn't say not possible. You cannot get any information out of. You can do. You can record solid state NMR of that. Okay. Immediately you can do that. Liquid is not possible because that is not soluble at all in any solvent. Solid state NMR record it. What you will get it? CH, a lot of CH band that will cluster at one place, giving a huge peak. If there is no functional group available, and if any functional group there, that will like 100% to 1%. You won't be able to even see that or characterize that. That will be a major challenge. Uh-huh. Ah, you know the fundamentals. I don't have to tell you that. When you have a paramagnetic compound, well, of course, NMR can be recorded. Nowadays, facilities are available. 600, 700 megahertz, you use it. But
Yes.
what you will get? You will get only broad peak because you have a paramagnetic center that will interrupt your or make your things almost like a corrupt. You will get only broad peak. What you will get? Only partly information you will get it, no other information. Okay. Yes, if you have a metal center and if you can record like EPR due to unpaired electron, and if you have a some diamantic metal center like vanadium, I told you that. Okay. Purposely, when I'm talking about vanadium, we are struggling with the 51 vanadium NMR. We had 400 megahertz facility, but we are not getting 51 vanadium NMR. वो क्या बोलते हैं, एनालिस्ट ने हाथ खड़ा कर दिया, बोले नहीं हो सकता साहब, मुझे आता ही नहीं है, ना हम कर सकते, ना स्टूडेंट पॉसिबल है. Okay. Then in 2017 we went to DST Fest. I was head of the department and tried to get 500 megahertz NMR purposely. And then before placing the order, I discussed with the person whether 50 NMR is possible or not. He said it will be possible. So we are getting all now 51 NMR, in our department, and I'm very happy. So because of that, I used to give at least 2 authorship in my paper, because simple as to go to different country, they are recording, giving the data. So now we are in our hand, we have that facilities we have. We are no less talented than the other any country people. I'm very sure in India we have plenty of talents. Students very talented they are, because the all facilities are available. Then go there, the outside see they do wonder. So now things are available, you can do that. So when you have a metal center, and if you can record NMR, oh yes, you can do that. Yeah. Any other question, please? Sure, please. You are the boss of the today. Yeah, you
Thank you,
can do
sir.
that, please.
Sorry, you have done a lot of work, and I have seen a very nice, means best molecule you have synthesized in your laboratory. And I need to ask, you have characterized the molecules by using the various techniques, and some of the molecules they are in crystal form. So uh, I have seen all the slides and seen all the molecules. They are more efficient, I think so, because you have synthesized and characterized. And I need to ask, these molecules can further applicable for biology purpose and other purpose. So I need to ask.
Yeah, definitely is a very valid question. When I gave you background, these are biomolecules. Okay, definitely. If I get one biolab which can collaborate, we can do them. We can prepare more complicated molecules. See, what I told you in the beginning, I'm a coordination chemist. I learned
Yes.
catalytic chemistry in between and doing chemistry. I'm a chemist, an organic chemist, converted to partly catalytic chemistry. Still doing a lot of vanadium chemistry than this chemistry. This is the side business. More the real business is something different. Definitely vanadium chemistry. Okay. So the our see aim was or is to do the chemistry. Okay. I leave the resting to biochemist, biological chemist, or other person who are doing such kind of activities. Okay. Well, of course, I can shake my hand, and if someone can help in screening these molecules, we can prepare even typical molecules, no doubt. Because since we are having limited facilities within the department, within what institute we have, uh, what are you saying that like simple metal complex itself, some molecules are very biologically active. You know, recently we just published last year, 2024 beginning one paper in inorganic chemistry. We collaborated with biosciences or bioengineering department. There we have done anti-cancer activity. That wonderful. Vanadium chemistry, vanadium compounds are very good. So we did for that, and we have published paper in organic chemistry. Simple molecule give very good results. We are able to publish it. Okay, but these organic molecules we have never tried it. The reason is limitations. We have a limited facilities. Within that, see, we cannot put our hands all over. Okay,
Yes.
कहते हैं ना, दो नाव पे चढ़ना और आगे का तो आप लोग जानते हैं, ठीक है, तो वो वाली बात है. तो बेटर टू स्टिक विथ योर केमिस्ट्री वेयर यू कैन डू बेटर. ओके, सो वी हैव ट्राई दैट, दैट्स ऑल.
Sir, if you have some molecules, final molecules,
हाँ हाँ.
characterized, because it is much difficult to re-synthesize. So, if you have and you permit me, I need some molecules because they are very much active for my purpose because I'm working. So, some
You send a student to the department. I will not come between you and your scholar and my scholar.
yeah,
You can have a 50 compounds.
yes, sir, very
They
good.
must be having that.
Thank
I'm
you
very
very
sure.
so,
If not, they can prepare it.
okay, so
Oh,
we
yes.
can do further process.
Yeah, of course.
Salim sir is doing theoretical chemistry. I'm doing
See, the
with
thing is what I said that with the limitations what we have and also constraints work within that, you cannot expand too much. See, for expansion you need collaboration there, definitely, because you cannot have all facility in the lab. The person who is bioorganic or bioorganic then he won't synthesize it because they are afraid of synthesizing. ये कहा बहुत सिंपल सर, नहीं नहीं नहीं, आप अगर आप दे सकते हैं तो ठीक है, मैं प्रिपेयर नहीं कर सकता. दिस इज द फैक्ट. Those people doing say anti-cancer or other activities, they need a molecule. They are looking for, आप दीजिए, हम नहीं देते हैं क्योंकि फिर वो स्टूडेंट हैज ए लिमिटेशंस. और माय ग्रुप, I set the parameters of 4 years. It should not go beyond that. Okay. So within that period, you work day and night. As you don't work, I don't mind. We need a result. And my strategy is that when you leave, your all thesis should be published. And better to publish in a good journals. That's all. And you will see that you have some feeling. That's all.
thank you, sir.
Okay.
So, thank you very much, sir, for giving for delivering the very good and informative and wonderful lecture. Yes, please, Shahzadi, Doctor. Sir.
My question is, how does the choice of metal like nickel, palladium or vanadium affect the reactivity and performance in heterogeneous catalysis?
See, now when you say comparison, I cannot compare it because I told you that I'm an organic chemist and more known as a vanadium chemist. Worldwide, I'm very well known. If you talk about vanadium chemistry, people take my name. Yeah, I can do vanadium. So I have tried in the beginning, in the very beginning, I tried with copper, nickel, cobalt, everything. Then I was not very happy. Stick with one metal, do something, world should know in that area. Okay, I have tried vanadium, to some extent molybdenum and tungsten, not more than that. When you look at my record in last maybe 15 years, I haven't touched any other metal. I didn't try. Otherwise, I won't say that nickel compound will not catalyze. Nickel compound will do good reactions. I'll show you some palladium compound next. I have slides from the other group also. I'll show you. They are doing very good. Palladium, see palladium compounds. Palladium compound, for example, in heterogeneous or homogeneous system, organic chemist, when real organic chemistry is there, immediately they will have a, they don't go for the metal complex formation even. They have a ligand, they have a metal, they mix it together, expecting they will form metal complex, do the catalytic activity. Okay, so they do the heterocyclic chemistry. So it's not, I'm not saying that the nickel will not work. It will give you very good result. When you look at the reason is why I choose this vanadium or molybdenum or tungsten. If you look at there, they are oxo group. For oxygen transfer and or in general say the oxidation reaction, they works very good. Okay, for the reduction or other reaction, see hydrogenation, reduction, others, you need different metals where normally they do not go for like forming oxygen bridging. You do not require there. They do the reactions. Heck coupling reaction is very well known by the using palladium
Yes,
catalyst.
I'm working, sir. I'm
Ah,
working on that.
head coupling. Plenty reactions you will find. Head coupling, palladium, 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 palladium. Whether homogeneous or heterogeneous. Okay. People ask me why you are not doing any reduction type of thing. I said, Baba, my catalyst doesn't go for the reduction. Go for oxidation, aerial oxidation, use oxygen source, use like hydrogen peroxide, use other oxidant to go for that. I found it one way to move further, faster. That's all. Yeah.
Sir, morphology of the polymers affect the catalytic homogenization heterogeneous.
See, definitely. If you add within the morphology, they that is called BET, surface area. Okay, when you do that, that gives you idea how much volume you have there where you catalyst approach to the metal center or not. Okay, like in catalyst, when you talk about this polymer beads, they are very hard. When you put in DMSO, this swelling occurs. Okay, when you swell, you have a pores available. I haven't shown any picture. I could show you. Pores can be seen through the morphology. Pores are available. They can enter right there quickly. If they can enter is easily reach to the metal center, it works better. So homogeneous. That's why the homogeneous catalysts are really, really good. The reason is, as soon you add into the solution, the metal center is easily available. Okay, but the only problem is that the what we call the recyclability, reusability, because it cannot be taken out from the solution. It is highly soluble in the reaction mixture. When you make it heterogeneous, there is certain condition. Whether your substrate is able to reach easily to the metal center. If it can reach easily, definitely that will work as a good catalyst. Simply. Okay? हाँ प्लीज प्लीज मुझे पता था आप एक क्वेश्चन पूछेंगे हाँ बताइए
As far as the catalytic action is concerned, with the vanadium complexes, uh, have you seen any difference between the paramagnetic vanadium complex and the diamagnetic
Okay,
vanadium complex?
I think you had a curiosity of paramagnetic diametric. I'll tell you that. See, these all reactions what I showed you, these are not like a reduction or anything. Everything is through oxidation, right? All reactions through oxidation. Now, when you are doing oxidation, you are using oxidant, maybe simple oxygen source, maybe molecular oxygen, maybe other oxidant like S2O2 or TBHP, etc. So, when you have a vanadium 4 like paramagnetic now, okay, for example, as soon you pass air, vanadium is very, very sensitive to oxygen. Vanadium 4 is very sensitive, though we think with one electron present in d orbital, vanadium 4 should be very stable, but it's not stable, highly unstable system. You know, sometimes what we have observed, I'm not showing you here the homogeneous chemistry. In a homogeneous system, we had vanadium 4 compound in one case, not in all case. We just simply grinded it in a, using pasteller mode. and it oxidized to vanadium 5. While recording magnetic property, prepared it today, after 1 week record the compound, magnetic property become diamagnetic. Second day you prepare, you have a half of that one electron going down, oxidizing. Once you pass the what see vanadium 5 compound, I tell you now, disclose it here, homogeneous system. Whenever we prepare the vanadium 4 precursor and we prepare only vanadium 4 compound, and when you convert into vanadium 5, either you pass simply oxygen, एरियल, ये आपने वो देखा होगा ना, फिश पॉन्ड, ये जो घर में लगाते हैं, क्या बोलते हैं उसे, एक्वेरियम, उसमें ऑक्सीजन बबलर है मछलियों को देने के लिए, वही बबलर हम लोग वेनेडियम कंपाउंड को देने के लिए यूज करते हैं. सिंपल सिस्टम से. दिस इज क्रिएटिविटी. माय स्टूडेंट, वी आर स्ट्रगलिंग फॉर. एस्पिरेटर लगा के पास करते थे, ढेर सारा पानी गिरता था, बच्चे मार्केट में गए, बोले सर ये बहुत बढ़िया काम कर रहा है, इसी को ऑक्सीजन सोर्स के लिए यूज कर लेते हैं. It worked. When I started this chemistry, vanadium chemistry, I failed at several instances कि vanadium 4-5 में जा नहीं रहा. The first, it took me almost 4 to 5 months to understand how this will go vanadium 4 to vanadium 5. रात को एक दिन फ्राइडे नाइट छोड़ दिया, सैटरडे संडे कुछ नहीं कर पाए, मंडे में आया तो देखा कि सरफेस पे ना ऑक्सीडाइज हो रहा है, समझ में आ गया, एस्पिरेटर से ऑक्सीजन पास किया, धीरे धीरे सारा ग्रीन कंपाउंड रेड में कन्वर्ट हो गया, समझ में आएगा यही है. वो दैट क्लिक डन दैट डे. इट वाज 1998 एंड नाउ हाउ मेनी इयर्स, 26-27 इयर्स. वो ऑक्सीजन अब सोर्स बदल गया, वो मछली वाला जो है ना वो आ गया यहाँ पे ऑक्सीजन पास करने के लिए. सो व्हाट इज हैपनिंग एक्चुअली टू योर क्वेश्चन, नाउ कमिंग बैक टू द 4, व्हेन यू ऐड ऑक्सीजन और ऑक्सीडेंट गोइंग टू 5 immediately, okay, and is doing the catalytic reaction. In some cases they come back to vanadium 4. So vanadium 4 paramagnetic molecule is also equally active like your vanadium 5 diamagnetic. Okay, only thing is it may be little delay, because when you are adding oxidant, it is converting from the 4 to 5, that much time it may require. So you may have some stagnation period. Ultimately, it gives you the same catalytic property.
As far as the stability of this polymer is concerned, diamagnetic material that is more stable.
No, not like that. I have shown you that vanadium 4 EPR. You want to go me back again? EPR, when you add H2O2 or oxidant, it is converting into 5, become flat, no EPR. When you add a substrate, oxygen is transferred and then it's coming back to 4. So stable, surprising to me also, to collaborator also, how this is stable, but it's really stable. It's going to maybe the ligand system what we had taken. In other case, it is going to 5 and become 5 because you are using oxidant. So it's stable in 5, but still it can be characterized very stable. Recyclability is there, but 4 is going to 5. So what we have tried to remove ambiguity, and maybe reviewer like you is stable 4 or 5, confirm it. We try to prepare 5 only. Okay, safe way to do it. Any other question? We have published almost 100 papers in vanadium chemistry. 25 years continuous, and still like this year and previous year we published paper in organic chemistry using vanadium chemistry. So I feel that still vanadium chemistry is going well after 27 years. We have still scope.
Thank you, sir.
Okay, thank you. Any other question? No question. Okay, thank you so much.
Now I would like to invite Professor Saif Ali Chaudhary and Salim Javed sir to facilitate our distinguished speaker as a token of respect. Please, sir.
भाई इस जगत में सर्वाइवल बहुत बड़ा काम है, ठीक है? अगर हम 20-22 साल से सर्वाइव कर रहे हैं तो कुछ तो कर ही रहे हैं.
सर इधर आ जाएंगे सर. सर यहाँ जी.
ये वही है कि हमारे मोबाइल में डालते हैं कोई लोग नहीं इधर नजदीक से मोबाइल पास से ले लो पास से आ जाओ इधर आ जाओ अरे बहुत लोगों के पास मोबाइल है भाई इधर आइए इधर पास से खींचिए तो पहले से खींचिए जैसे हम चार लोग पीछे से भी आ जाए लास्ट लाइन वो भी आइए थोड़ा इधर हो जाते हैं हमारी दो फोटो आएगी चलो आप प्लीज दो बंद हो जाएगा Thank you. Thank you, sir. Thank you. It's my favorite. Actually, past 25 years. जी जी आप आए अभी कभी yes हम लोग छोड़ना नहीं याद रखते हैं बहुत अच्छे रिलेशन